Okay, let's get started. Uh, so okay, so as I mentioned, so we will take the midterm exam on the next Tuesday, right? During the regular class time. Okay, and then so we will take the exam in this class in this classroom, right? Uh, okay, and then the exam will cover chapter 1, 2, and 3, right? As I mentioned. And then, okay, so this is the closed book exam. And then the difficulty level of the exam can be similar to the difficulty level of the homework assignment. Okay, so I believe if you can understand and then and if you can answer homework questions by yourself, then I believe you can get good scores on the midterm exam. Okay, so and then also try to understand some important concept in what we learned. Okay, so in the chapter 1, 2, and 3. So actually in chapter 3 we learned about the hardware structure and then floating point floating point number format, right? And 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 then but this exam will mainly cover chapter 1 and 2, and then I believe maybe only one question will be asked in the chapter 3. Okay, so and then the main chapters are chapter 1 and 2, right? So and then in the chapter 1, you need to understand how to measure, how to compare the performance of two systems, right? So actually, I explained that in order to measure the performance of on one system, so actually we need to compare the performance with the baseline. Okay, so so in chapter 1, so you need to calculate. So you need to compare the performance of two systems, right? And then in chapter 2, so we learned about the instruction set architecture, and then we learned how the high-level language codes are translated into the machine codes. Okay, so so you need to understand. You need to understand how the instructions are uh, translated. So which means that how instructions are executed in a processor. Okay, so you need to understand the result of assembly instructions. Okay, and then so as I mentioned, so you don't need to remember some encoding or decoding rule of the between the assembly instructions and machine code. Okay, so if required, so I will provide these encoding and decoding rules between the assembly instructions and machine code. Also, if required, I will provide some instruction list. So in the homework assignment number 2, so you can find some instruction list, right? So like this, then I will also provide some instruction list, the RISC-V instruction list. So you don't need to remember, you don't need to memorize some this information, okay? Like the instruction list or some encoding and decoding rules, okay? But you need to understand how instructions are decode, so executed. So it means that how instructions generate the result in the processor, right? So uh, actually these are main topics. So we learned in the first half of this course, right? Okay, so so even though and then we will move on to chapter 4, the processor. So this chapter 4 will okay. Uh, no, actually, not no, actually. So I may ask some, but I don't think so. So actually, so I mentioned that. So the midterm exam will cover the lab 1 and lab 2, but so I will not. So usually I will not ask some uh some processes. So like the somehow install the some compiler. So this will not be asked in the exam. Okay, so it's not. So this is the some Selenos analysis. So usually, so and then mainly, the exam will cover chapter 1, 2, and 3 only. Okay. So actually, in the lab, so so actually lab assignments are designed for students to understand. So to make students understand how instructions are really translated by compilers. Okay, so actually, uh, okay, so you so you need to understand some conceptual view or conceptual information, but you don't need to as I mentioned, you don't need to memorize, or you don't need to uh, you don't need to memorize some processes in the lab. Okay, so actually I don't like the memorization. Okay, I don't know actually, but usually uh 5 or 6, but so so like the homework questions. So actually, so in the some in the question, there can be several questions also. There can be several sub questions, right? So like the homework, and then usually in the exam, so there can be 5 or 6 questions. What these questions may include some sub questions usually. Okay, so similar to, so actually the exam questions are similar to the some homework questions. So homework questions. Okay, any questions? Okay, and then also the this, this is the English course. So the exam questions will be written in English, but you don't need to answer in English. So for Korean students, you can answer in Korean, right? And then so you can use any languages for answering the questions. Okay, so and then usually uh, mm, okay, so and then sleep early. So you need to so for, actually, and for Korean students, so you need to translate the English questions, right? So and then so and then so sometimes so you need to translate you need to understand some exam questions very quickly. Okay. Okay. Uh, okay. So in chapter 4, so actually, but this chapter is a very important chapter in the computer architecture course. Okay. So chapter 4, we will learn about the hardware architecture. So it means in chapter 2, we learned about the instruction set architecture. So instruction set architecture defines the instructions used by a processor. So as I mentioned, so so in chapter 2, we learned about this concept. Okay, so instruction is given to a processor, and then the processor create the result of instructions. And then I mentioned that the result of instructions are defined in ISA document, the instruction set architecture document. But you need to understand that instructions change architectural state, as I mentioned, and the architectural states mean register file, so value of registers, and it can change main memory, like the data in main memory, but usually only the store instruction. Okay, right? What happened? Only store instruction. Store instructions change the main memory, and then other instructions such as arithmetic, logic, also load instructions, and then uh, these instructions change the data in registers. And then branch instructions. Branch instructions change program counter. The program counter is also a special register, right? So the program counter is a special register in a processor. So you can understand that branch instructions change program counter registers. Okay, PC register. Okay, so the result of instructions are defined. So defined by ISA document, and then so we need to, so in order to execute instructions in the real world, okay, so we need to design a hardware, so real hardware processor. So in chapter 4 we will learn how processors are designed. So we will learn about the hardware architecture, so real hardware architecture of a processor. Okay, so this figure shows the layers layers in the computer system, right? And then I mentioned that in this course we will learn about the architecture and the microarchitecture of computer system. And then, so in chapter 2, yes, this is the chapter 2. So in chapter 2, we learned about the architecture. So it means the instruction set architecture. And, and then in chapter 4, so we will learn about the microarchitecture of a computer system. So microarchitecture defines how the hardware processor hardware is designed. Okay, so microarchitecture defines how the the processor hardware is designed, right? So ISA ISA designed ISA designs the instructions executed by a processor, and microarchitecture microarchitecture defines the hardware architecture, the hardware design of a processor. Okay, so and then when we design a processor, the real hardware, then we need to also consider the performance. Okay, so in chapter 1, we learned about the performance of a computer system, and then, so what is the purpose? So what is the goal of this hardware design? So introductory class, so I explained, so I mentioned that everyone wants to use good computer. Okay, so it means good means that a good computer system means a faster computer. So that means that the performance is high, and then the cost is low. So these are the goals of the hardware design. So we need to consider the performance factors. Okay, so and then usually in the hardware design, so instruction count. So what is the so you need to remember this equation. Okay, this equation will not be provided in the exam. What is the execution time? This is the instruction count and CPI and TC. So TC is the clock period. And then I explained that instruction count is the software part, so it is defined by software code, and then usually the hardware, and then I mentioned usually, not okay. Usually hardware determines CPI and clock period. Okay, so when we design a processor, the processor hardware, so it means we need to consider the CPI, the clock per instruction, and clock period. Okay, so you need to understand this equation, and then also you need when when you learn about this hardware architecture, then you need to consider these factors: CPI and TC, the clock period. And then also, so we will use the RISC-V instructions, obviously, but so we will use a simplified version. So I will not explain about some all baseline instructions of RISC-V. Okay, so actually in in chapter 4, so I will use a part of RISC-V instructions. Okay, so these are instructions which will be used in the chapter 4. So as you can see, so we will use the load and store instructions, load word and store word, and then some arithmetic and logic instructions like add, sub, and or, and then control instruction, the branch instructions, BQ. So using these instructions, I will explain how how a RISC-V processor is designed. Okay, but so this is the simplified design. Okay, and then so actually in in the undergraduate course, so we will learn about very simple processor design. Okay, uh, the modern processors such as Intel's AMD CPUs, also the ARM CPUs, and then the Apple CPUs. Modern processors actually use some more complex. So the more complex, and then the the so and then also modern processors use different architectures. Okay, so I mean the more complex, and then using this more complex architecture, and then modern processors exhibit the higher performance. Okay, but this is the undergraduate course, so we will learn about the very simple processor architecture. Okay, so pipeline architecture and a single cycle processor architecture. Okay, so in chapter 2, we learned how instructions are executed. Okay, and then so now we learn about the inside of a processor. So which means that a processor needs to generate the result of instructions based on the input instructions, right? So, and then I mentioned that the result of instructions are changes of states, the architectural state. So it means, so it will change the data in register file, and then data in main memory. Okay, so and then so it means we need to design a hardware that can change the register file, and then they can update the main memory based on the instruction. So then let's see what is required. So what is required for executing instructions, and then what is required for design hardware that can execute instructions. So I believe you can understand. So this is the PC. Okay, so let's review how instructions are executed. So this is the PC, and then so you can find some machine code, so like the instructions. But actually, it's it is difficult to understand this machine code instructions. So I will use the assembly instructions instead, like the assembly instructions. So we learn. So actually, in order to execute an instruction, then a processor needs to set program counter. So you can observe in the compiled code, you can observe the program counter and then the translated uh, instructions. Okay. So let us assume this is the PC is the 0, 0, 0, 0, and then the instruction is the add x1, x2, x3. And then the next instruction is 0, 0, 0, 4, and then sub x3, x4, x5. Okay. So then let's see which steps are required for executing instructions. Firstly, so I mentioned, so we learned that instructions are in memory, right? So instructions are also data, and then instructions exist in memory. And then in order to access these instructions, we need to set an address, right? In order to access the data in memory, so we need to set an address. And then I mentioned that the program counter is an address of instructions. So which means first step, the first step is to set program counter, set a program counter. Okay. So in this example, in order to execute this instruction, add instruction, then a processor needs to set program count value as 0x0000. So first step is to set up program counter value. Okay. And then using this program counter value, program counter data, so where is the instruction? The instruction is in memory, right? So using this PC value, then a processor needs to access memory. Okay, access memory. It means that read memory using a PC. So this process is called fetch. So this process is called instruction fetch. So fetch or fetching fetching an instruction. Okay, so it means you can set PC value, processor can set PC value, and then using this program counter value, then a processor accesses memory to read an instruction. So this process is called instruction fetch. Okay, so the first first required step is instruction fetch. Okay, then what is required? So instruction is is a binary data, right? So even though I used this assembly instruction, but actually so the instructions in a memory is the binary data format, right? So like the 0x, so this is hexadecimal number, but it's binary, it's a binary number. So like a 0 1 0 0 0 blah 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 0 0 0. So in order to figure out the format of instructions, a processor also needs to decode. The processor also needs to analyze. A processor needs to analyze this machine instruction. So in the chapter 2, we learn how assembly instructions are translated or encoded into machine code. Okay, so if assembly instructions are encoded into machine code, then machine code has the binary data format, right? And then actually this binary data is is stored in the memory, so it exists in memory. So this binary data will be read from the memory. Okay, so in order to figure out this instruction format, a processor needs to analyze or analyze or translate the machine code. So this process is called the decoding. Okay. So encoding means that the assembly instruction is translated into machine code. Decoding, the machine code is analyzed and then figure out the assembly instruction. This process is called the decoding. Okay, so the machine code, the machine instructions need to be decoded in a processor. Then a processor can figure out, oh, this is the add instruction. So this is example. So add instruction, or this is the R type instruction, right? Because and then so if we decode the this machine code, then then destination register RD register number is 1, and then RS1 is 2, RS2 is 3. Okay, so we learned about the encoding rule. So decoding is the inverse process of encoding. So by encoding the machine code, then a processor can figure out, oh, this is the add R type instruction, and then RD is 1, RS1 is 2, and then RS2 is 3. So this step is called the instruction decoding. So instruction decoding. So instruction decode. Okay, so it is instruction fetch and then instruction decode. And actually, so this is the R type instruction. And then in order to execute this instruction, then what is required? Operands are required. So in this example, this instruction add x1, x2, x3 requires the source register data, right? And then where is this data? In registers. Okay, so this is in the x2, this is in the x3, right? So a processor needs to read data from registers. Okay, so the processor needs to read data for operands. Okay, so in this example, we use the R type add. So RS1 or RS2 data needs to be read from registers. Okay, so register read. The register read is required. Okay, but usually, actually, this first step is called the instruction fetch, and then so instruction decoding and then register read is just grouped, and then we just call this is the instruction decode. Okay. Then the third step. So what is required? So a processor figures out the type of instruction and the operands are ready. So the source register data are ready. Then we can execute. So this is the add instruction. So add instruction, and then the operands are ready. The operand data are ready, like the uh, RS1 and then RS2. So these data are ready. And then which operation is required? Addition. The addition is required. That's why we learned about the adder in chapter 3, right? So the execution unit. So this is the this all the arithmetic units are also called execution unit. So using this hardware component like the adder arithmetic unit, then we can generate the result of this add instruction. So this is the result. Okay. So this operation is also required. Okay. So and then this is called the execution. So instructions. So I explained about the instruction fetch, decoding, and execution. So the data are ready, so which means operands are ready, and using a hardware engine, hardware execution unit, then a processor can generate the result of instruction. Then what is required? So if we analyze this instruction, the result of the result of add needs to be stored in destination register. So this is the final result. So I explained about this. So change of states. So this is the result of instruction. And then the data, the result is stored in registers. Okay. So the required step is to store result in registers. Okay. So this process is called write back. So it is because actually in the registers, in the source registers, instruction read data. Okay, instruction read data from source registers, and then result is stored finally. So the result is written back to the registers after the execution. So this process is called the write back. Okay, but actually the required step before this write back, actually this execution part, the execution part is execution part can be different by instructions, right? So for example, memory instructions like load word, the load instructions, then this load or also the store word instruction. This load and store instructions need to access memory. Okay, so which means that the execution part is different. So for example, the arithmetic instructions such as add, sub, and then some other instructions, these instructions require the arithmetic unit. So we learned in the chapter 3, these instructions require arithmetic units to generate result. Okay, but some other instructions such as the load instructions and store instructions, these instructions need to access memory. Okay, so which process is required? Using a calculated address, okay, then these instructions needs to access memory. Okay, so this is also required. Then how about the branch instructions? The branch instruction is also different. The branch instructions need to update program counter, right? So program counter value is changed by branch instructions. Okay, so based on the instruction types, then the execution part can be different. So this is the execution, but uh, in this process of design of this course, this is called the memory part, memory step. So which means that if the instructions access the memory, then this step is called the memory step. Okay, so this step is also required. And then finally, the registers, like the add instructions, also the load instruction, then the arithmetic instructions and the the load instructions change registers, and then as I mentioned, this step is called the write back. So these are required steps. These are required steps for executing instructions. Okay, so actually, software view, the software view, so we can simply understand instructions like this. Okay, and then so which means instruction like add x1, x2, x3. Then it performs the x2 plus x3, and then it is stored in the x1 immediately. Okay, so we can just understand. So in a software view, then we can understand instruction execution like this. Okay, that's what we learned in the chapter 2. But actually, inside of a processor, so in order to execute instructions, then these steps are required. Okay, and then it means in order to design a processor, then the processor hardware needs to support these steps. Okay, and then the processor architecture will be designed based on these steps. Okay, so this part is a very important. So these are so required steps for executing instructions. So you need to understand these steps. Okay, and then the hardware will be designed based on this operation. Okay, and then before learning about some hardware architecture, and then let's learn about some logic design convention. So this is somewhat review of the digital logic design course, but this knowledge is also required for understanding hardware architecture of a processor. Okay, the logic design. So as I mentioned, the CPU is type is a kind of a digital system. So which means a CPU can only understand digital signals, and then digital signals are composed of only 0 and 1. Okay, so only two values, and then 0 is represented using low voltage. So actually we use the voltage level to represent different binary values. The low voltage, like the ground. So this low voltage represent the value 0, and then high voltage, like the supply voltage VDD, and then this high voltage represent the data 1. So by using this, then a CPU can figure out the data. Okay, so this is the some binary data. Okay, and then uh digital systems. Digital systems just receive the digital data and then also generate the digital output, right? Obviously, right? So actually inside of this digital uh, system, actually we can implement the digital system using digital circuits. So like using the CMOS circuits, but and then CMOS circuit just interpret the high voltage is 1 and the low voltage is 0. But this, as I will explain about this. Okay. So you can just understand the digital system. This the system like this. So this is so it's actually it's very simple. So this is the input and this is the output. So the system just to receive the binary input and then generate binary output. So we can just define the function of a digital system. Okay. So which means the output is the function of input. Okay. But these data are just binary data. So we can understand the digital system like this. But this is the hardware. So we need to consider some other aspect because hardware runs in real world. It's not software. The hardware runs in real world. So actually, it takes time. It takes time to generate the output. Okay, so you I mentioned that you need to understand that this. So this is the some this is the gap or some this is the difference between software and hardware. The software does not consider time actually. Okay, so we can notify that when we run a binary file it takes time, but actually when we write a code we do not consider how much time will be taken. Right. We just write the code, and then we assume that this code, so each instructions will be executed immediately. Okay, but actually, hardware also receives input and then generate output based on the function. So this is the same, but after data t, so delay. So actually, so you need to understand this concept. Okay, this is the system, this is the hardware. So actually, this is same. The input is given and output is generated, but after some time, after delay. Okay, delta t. So this is the um this is the component we need to consider for designing a digital system. Okay. So also I mentioned the combination element and then the state element, sequential element. So by combining the combinational logic and sequential logic, then we can build a digital system. Okay. So I will explain later. So this is the combinational element. So it's a basic gate. Okay. Basic logic gate. So it's an AND gate and the adder and then multiplexer and then arithmetic and logic unit. So actually, I will not explain about. I will not explain, but So you can just, I believe you can easily understand. So actually, so as I mentioned that, this the system, the output is the function of input, right? So if you see that this AND gate, the function is the AND. The inputs are A and B. So F A comma B is the Y, but and then this function is the just bitwise AND. Okay. So, but you also understand that this AND gate also has delay. So this output, the output of AND gate will be generate after some delay. Okay. So you can the combination element, in the combinational logic, you can just understand like this. So this is the function of the combinational logic generate the output based on the functions of input signals, but after some delay. Okay. So which means if the input values are changed, then output values are also changed, but after some delay. Okay. And it's the same. So you can just O equal F of A comma B, and then F is the addition. Okay. But after some delay. So you can understand the what happened, the combination logic like this. And then what is a multiplexer? The multiplexer means that based on this selection signal, then the Y output, Y, the output Y becomes one of inputs. So which means that the Y, the output Y can be I0 equivalent to I0 if the S is 0. And then if the Y can be equivalent to I1 if the S is 1. So this is the function of a multiplexer. And then you can I believe you can understand that this function. This is the C representation, right? And then this is the ALU, arithmetic and logic unit. So this is the combination unit. And then we can design this combinational logic gate using system Verilog. So, the system Verilog is the HDL, the hardware description language. Okay. So actually, for upcoming labs, so we will use a system Verilog to design the processors. Okay. So, this is the example. Okay. So it means that this is the module name, and then it represents that this module has 3 ports. Okay. So port. So port means that this is the input and output of a module. So you can just understand the module like this. So this is the input port, and then this is the output port, right? And this is the module. Inside of the module, we can define the function of a module. So it means it represents there are 3 ports. So A, B, Y. Okay, A, B, Y, and then you can define the port type. So this is the input type port. A and B are input type port, and then Y is the output type port. Okay, and then we can define the function of this AND gate, and then function is really simple. So we can just use the AND gate. Okay. So adder. So so we can also define the 3 port, and then this is the some vector type port. Okay. A and B are vector type port. So it will generate it will receive the 8-bit data, and then it will also generate the 8-bit output signal. And then we can also define the adder simply. So this is what we already done in the lab 1, right? y equal a plus b. So we can just define the function of the combinational logic. So this is another example, the multiplexer. Okay. And but we also need to understand the sequential logic. Okay. So in chapter 1, so I mentioned the clock signal. Okay. And then we also learned that the clock signal, the clock period determines the performance. It means because the execution time is the instruction count, CPI, and multiply by clock period. So actually, the every digital the the digital system requires clock signal. So the clock is the periodic signal, and then it just to repeat the up and down, like so, like this. So this is the clock signal, and then clock signal, the value 1 and then value 0 are repeated. Okay, 1 and 0, and then this period, the period is the same, the fixed. So within a clock period, the clock repeats. The clock has the two values, 1 and 0, and then these 1 and 0, this pattern is repeated again and again. So this is the clock signal, and then so you can just observe the clock period. So this clock period determines the performance. So it means the execution time of a system. Then why? Why? So I mentioned that. So we are just assume that we just assume a processor can execute an instruction per clock. So which means that a processor can execute an instruction within a single clock period. So just a very simplified assumption. It's not always true, right? But this is just a very simplified assumption. Okay, but it is because the design, or CPU is also designed based on this clock signal. So like a sequential logic. Okay. So you can find, so actually, this is the system we implement the sequential logic using D flip-flop. So and then this is so you need to understand this behavior of D flip-flop. Okay. So D flip-flop has one D input, it means the data, and then one output is the Q. Okay, this is the data output. And then, but also you can find the clock signal input. Okay, so this is the behavior of D flip-flop. So at the rising edge of clock, D flip-flop samples this input value. And then this, after some delay, so this is also hardware, but you can just understand that this sampled value is maintained within a clock period. And then clock signal is the repeated signal. Okay, so we can also observe another rising edge of a clock here, right? So which means at this time, at this clock rising edge, then D flip-flop just samples input value D. But you can find that, oh, the value is changed here, right? Then this changed value is reflected to the output. And then this output is also maintained within the TC. Okay, so this is the behavior of D flip-flop. So you can observe that uh, the input is changed within this clock period here, but the Q is not changed because the Q just reflect this sampled value only. So this value is only reflected to this Q during this clock period, and then so this operation is repeated. So this is the behavior of deep flip-flop, and then we use these deep flip-flops for implementing digital systems. So it is because okay. So it is because so I mentioned that the combination logic is the F and then I and O, and then the out the output is determined the output is updated by this input value after delta t delay. But this delta t is different by different logic, obviously, right? Because we need to build the combination logic using the digital circuits, and then the delay is different. The delay can be different by some environment, such as the temperature, and then the process, and then some other factors. So actually, this delta t can be changed. Then what is the problem? Actually, our system, like the CPU, is very, very complex. So for example, in order to execute instructions, CPU needs to perform these steps, these multiple steps. So actually, we can implement these steps using digital logic, like combinational logic. But what's the problem? Delta T can vary. So delta T's are different. So in this case, so it is very difficult. It's very difficult to control the flows of signal, right? So we design this the system using deep flip-flops. So using deep flip-flops, so we can just set the timing of data based on the clock signal. So which means we can control the timing of signals using the theoretical clock signals. Okay. So what does that mean? Let's think about the okay. So I'll use this slide. Okay. So we want to perform the different function like F1 and F2. And then actually the same input is given to F1 and F2. And it will generate the different output, O1 and O2. Okay? But this F1 will generate the O1 after some delta T1. And then F2 will generate the output O2 after delta T2. And then this delta T1 and the delta T2 are different. And then after some time, some combinational logic may use this O1 value and O2 value. Okay, we can just we can just connect these combinational blocks again and again. Then we can just generate the more complex logic. Okay, but problem is that because the delta T1, delta T2 varies, so those delta T1 and delta T2 are different. So we cannot figure out how the O1 and O2 will be given, when O1 and O2 will be given to this F3 combinational logic. So we cannot control the timing of input for the next step. So in this case, so if we cannot control the timing of some functions, problem is that we cannot we cannot build stable system. Okay, so right, obviously. So in a real world, so in a real world, if we cannot control the timing of a system, right? Like so, like the class timing, then actually we cannot build stable system, right? So there are many students, but the class time is just start at the same time for many students. So it's called the synchronized. But if we cannot control this timing, then the many students will come to this classroom the different time, right? So this is the unstable system, right? So this actually the hardware works in the real world. Okay, so the signals, sometimes the signals to some function is to be synchronized. So it means that it's controlled. Okay, so using D flip-flops, we can control the timing of signals. Okay, that's why we use the D flip-flops, and then we use this clock signal for building the complex processors or complex digital systems. Okay, so you need to understand this concept. So actually, we build the digital system like this. So you can observe that this is the state element 1 and this is state element 2, but this is actually D flip-flop. This is the another D flip-flop. And then you can observe the combinational logic between the D flip-flop. So you can just so that there can be multiple inputs, and then this is the combination logic. This will generate the multiple outputs. This right? So and then clock signal is here. So clock signal is connected to the clock port of this D flip-flop, and then it's connected. So we can design the digital systems like this. So why? So because this combinational logic receives the synchronized input from this D flip-flop. What does that mean? The input signals are synchronized. The input signals are provided to this combinational logic at the same time. So like this class. So this class starts at 10:30 to the multiple students. So it's synchronized. Okay. So the input is provided to this function, and then this function will generate multiple outputs. Okay, so multiple outputs at the different delay, delta T1, delta T2, delta T3. And then these outputs also need to be provided to the other functions, the other steps, right? So in order to synchronize this timing control, then these outputs are also sampled by another D flip-flop. Okay, so we can provide the synchronized signal to the next function block, like next combinational logic. That's how the digital systems are designed. Okay, so so you can find that. So there are two D flip-flops. So and then this D flip-flop provides the input signals to this combinational logic. And then this D flip-flop receives the output from this combinational logic. Okay, and then this is the clock signal. Okay, that's how we design a typical digital system. And then CPU also works like this. So it is because the CPUs are very complex digital system. So it means that we need to use the large amount of, the huge amount of digital logics, digital components. So we need to synchronize. We need to synchronize the the signals. We need to control the timing of signals. So, and then, but there is a timing constraint. So in order to make this system stable, the critical delay means the slowest delay. It means the largest delay of this combinational logic. So the critical delay of this combination logic needs to be lower than the clock period. This is very important. So, so think about this. So if the delta t, the delay is larger than the tc, so what will happen? Unstable output value. Unstable output value will be sampled by this D flip-flop. Then this D flip-flop will provide the unstable values, right? That's the problem. And then, the CPU generate the incorrect values, then it's a problem. It's a critical problem, right? So this is the very critical rule. So this is the very important timing constraint, the delta t. The delta t of this combinational logic, so this is critical delay, needs to be less than the clock period. Okay, this is very important rule when we design a hardware component. Why? Why is this important? So it means actually the delay of this combination logic determines clock period. Right. So let us assume that you are design a combination logic, right? And then your design exhibit the 10 nanosecond of delay. Then the clock period needs to be larger than the 10 nanosecond, like maybe 9 nanosecond. Then the clock period needs to be larger than this 9 nanosecond, for example, 10 nanosecond. Then this is the clock period of this system, right? So actually we need to reduce this delay in order to improve the performance of our system, our CPU, right? That's why this concept, this timing constraint is very important, very critical for hardware design. Okay, so I hope you can understand this. Okay, so this is the example code of the D flip-flop. So you can I also posted some HDL design, HDL design lecture. So in the digital system design course, digital logic design course, right? You can also watch the posted video. But so this is the example of the deep flip-flop. Then this is the deep example of deep flip-flop with the asynchronous reset. Okay, so please watch. So if you did not take the digital logic design course, then please watch the posted video. Okay. Okay, and then so let's so, so if you generate the latch like this is bug. Okay. So what's the problem? So this is also the combinational output. So based on the condition, then we can just define the output of the combinational logic. So, but the problem is that so if we use the always underbar comb, so this means that so we will design a combinational logic. But if we just use this conditional output in the combinational logic, then we need to define all outputs by all possible conditions. Otherwise, HDL, the system Verilog, this system Verilog code will generate the latch. And then, but latch is the, usually in a digital system, we do not use latches. So it means bug. It's a bug in the hardware design. Okay. So you need just remember that. So in a combinational logic design, and then if we just define the output values based on some conditions, then we need to define outputs of all possible conditions. So in this example, En is the 1-bit signal. So that which means that it has the 1 and 0. Those are all possible conditions. So which means we need to define the output for input 1 and input 0, all possible conditions. But in this example, I just define the output by this one condition. Okay, the part of conditions. So this will generate latches, but if the latch is generated, then it's a bug. Okay, it's a hardware design bug. Okay, so we need to avoid bug, right? Okay, so so this is some basic concept of digital design. Then so because we are moving on the some hardware design, so which means you need to understand how the digital systems are designed, right? So uh, so that's why the digital logic design is the prerequisite course of this course, right? But hopefully, even though you did not take the digital logic design course, so I hope you can understand that this important concept of digital design. Okay. Okay. So I will stop here. So any questions? And see you in the next class. So and then good luck for your midterm exam. 감사합니다.